Welcome to our session on electric machine control strategies. And I'd like to introduce Jan Richter, who's come all the way from Germany, from the Karlsruhe Institute of Technology. So Jan, please come to the stage. Thank you.
All right, thanks a lot, Chloe, for the nice introduction. Just a couple of words to my expertise. I'm a researcher. I work at the university, and I deal with the modeling, perimeter identification, and control of permanent magnet electric machines. So the talk today is really on my research field, but I try to break it down and really give some little topic that might be, at least I think, interesting to you guys. So let's get into it, and I want to really start off with a short outline of the whole topic. So we know permanent magnet synchronous machines for decades, and we know microprocessors also for quite some time. So to me, it seems like to be a fair amount of time to basically solve any problem in this whole area. But obviously, still today, we have industrial development going on, we have research going on in this field, and there are different drivers for that. And two are given here on the slide. The first is that we really see a decreased rate-to-power ratio of these modern electric machines, and it's given in the graph right here. If you go back 10, 15 years, even today, industrial drives, induction motors, or permanent magnet machines are in the order of 10 kilograms per kilowatt machine power. If you then look at automotive traction motors, this got significantly reduced to below 1 kilogram per kilowatt power. And the motor here, right on the bottom right slide of the part of the slide here, that's a Formula One race car motor. The electric engine that is built in the kinetic energy recovery system, it has only 200 grams per 1 kilowatt machine power. And there are different reasons how we could get that done. How could we significantly reduce this rate-to-power ratio? And two examples are given here, just use higher rotor speeds. And that's why that's on the x-axis here. And another reason was higher utilize the machine materials. So we use higher current densities together with a better cooling, fully saturate the ion in the machine. These are the main drivers for that development. All right, the second thing that made really pushed control of these machines is self-sensing control. I mean, the motivation is obvious. We want to get rid of the angle and speed measurement. And this has been researched, again, for decades. It's an old topic, but still today, to whatever conference you go, there's always 2 or 3 sessions on that topic, still not completely solved. Not for any operational condition, not for any machine. Yeah, it's still an issue. And my talk today is not on self-sensing control. It is not on this higher rotor speeds. I picked another topic. And what I want to talk about today is this higher utilization of machines' materials and the consequences for machine control. So this is the focus on the talk. How do I want to do this? I want to really start off from the scratch and develop together with you guys the linear model of such a permanent magnet synchronous machine, and then show that there are two effects in these machines, acceleration and cross-coupling, that cause the linear equations not to be valid anymore. And then I want to show how you can get these effects into the equations. After that, we have a model, and the model has parameters. So we have to identify these parameters. That's what I want to do next. And then we can use this model to actually control such a machine. And if you look at approaches from universities or industry, some people come up with really fancy control algorithms. And what I want to do here, I want to really keep it simple and show that these machines can be successfully controlled with high performance with a standard PI controller, with just adding some smart lines of code to deal with these nonlinearities. All right, and of course I conclude with a short summary. So let's get into it. What are my basic assumptions? I have a 3-phase motor with a symmetrical winding. The neutral point is not connected to the inverter, and for now, ion losses, friction, dielectric currents, temperature effects, and spatial harmonics are neglected. This doesn't have to be done. I just do this here for simplicity. Just in Berlin a couple of weeks ago, I gave a talk on ion loss and friction can be easily included. There are a lot of temperature models out there that you could use to incorporate that in models. As a matter of fact, I also have some backup slides about spatial harmonics. If you're interested in that, we can discuss this after the session. Just ask that. All right, in order now to develop this model with these assumptions, I need some formulas, and I have to put some equations on the slides. I promise it's just 2 or 3 slides, just a couple of minutes. But if you follow, it's going to be really worth it. So we then just start off and look at the machine and apply basic fundamental physical laws, which is Ohm's law, Faraday's law of induction, and the Kirchhoff laws, to the machine coils. And what you end up with is a simple model of such a machine, given in the form of an equivalent circuit right here, or in form of an equation here. So what's basically standing here is that the voltage in one coil is the sum of the ohmic voltage drop and the induced voltage. That's it. And you'll have this equation for 3 coils, because you have 3 coils in the machine. But it would be a lot better if you would only have 2 equations, right? It's just easier if you just have to deal with 2, and this is possible. You don't lose any information if you reduce the order of this system by 1, and this is done by a transformation, and that is called alpha-beta transformation. The equation is given here, not so important. Maybe look at this little sketch right here to understand what we actually do. We have 3 coils in the machine, and there's an angle of 120 degrees in between them. And any space vector of the machine is like a vector in this plane. So we can also represent any vector as a linear combination of these 3 vectors, or simpler, as a linear combination of a 90-degree angle system that we call alpha-beta system. That's the idea. So if you just substitute these equations into these ones, you end up with a system equation in the alpha-beta frame, and this is given here. These values are underlined. That means that that's a complex number. So these are actually 2 equations, and that's how we got the order reduced by 1. But you can see by doing that, basically nothing changed. Still, the sum, like the voltage sum of each coil, is the sum of the ohmic voltage drop and an induced voltage. If we look at this equation, and we operate the machine stationary, that means that all these quantities, like voltages, currents, and flux linkages, they change all the time. If you just consider the fundamental component, they would change sinusoidal. Yeah, that's not so good. It would be a lot better if all these quantities would be constant during stationary operation. And this is why we look at permanent magnet synchronous machines in a rotor-orientated, rotating reference frame. And this is done by another transformation that is called the DQ transformation. Again, the equation is given here, but just look at like the little sketch to understand. This alpha-beta frame is stator fixed, and this DQ frame is rotor fixed, and this turns all the time like fixed to the rotor. And if you now apply this equation like to here, you end up with the system equations in the DQ reference frame. And here you see something changed. The equation looks a little bit different. So why is that? It's because it's the product rule of differentiation. So we have to here differentiate the flux linkage, which is now a product of 2 terms, and that's why it gets split up into these 2 things. What stands here is like the voltage in the DQ reference frame is the sum of the ohmic voltage drop plus an induced voltage due to a flux linkage change due to a current change plus the induced voltage due to rotation. So 2 physical effects, an induced voltage due to a current change, an induced voltage due to rotation of the rotor got separated by this transformation. And this is nothing new, by the way. The guy who first came up with that was Mr. Park. Some of you might know him. It was 1929, the Park transformation. He directly transformed the stator quantities in this DQ reference frame. All right. Again, I said these are actually 2 equations. So now let's split them up in its components. You can see that here. This is a complex phase vector right here, x. And you can look at it. And it's each component, the D component and the Q component. And these are the 2 equations that I will use in the following in this talk. This is the general system equation for such a permanent magnet synchronous machine. And what we then do normally, at least with our students, we say, well, our machine is linear. We have linear magnetics. And that means that the flux linkages depend linearly on the currents as given by the equations here, or like this is the sketch. This is just a straight line. That means linear magnetics. If the current is 0, you still have some flux linkage left. Yeah, this is the permanent magnet flux linkage. And this is it. You can just put like that in these equations, and you end up with the linear system equations that some of you probably know. And this is where university, like when we teach to all the students, where we usually stop. But now I said, if we have like these real light machines, small machines, and we highly utilize the materials, these equations are wrong. They are not valid anymore. So in the next 2 slides, I want to explain why this is the case and how can we fix this problem. The first effect that causes this equation to be wrong is saturation. Obviously, we use iron in these machines, and iron You can think of iron of having like these microscopic little magnets, and they are all aligned in the same direction in some sort of area. In between are these block walls, and at some point, all these microscopic magnets might be aligned in this exactly the same direction, and then the iron doesn't amplify the flux anymore. And this can be easily measured. This is a real measurement in an Epstein frame of such a metal steel sheet. You can see the linear area, linear operating area, where the flux is amplified, and then at some point, the iron is saturated, and the amplification is just over. How can you model that in like this electric motor model? And this is like one of the major messages of this talk. Well, if saturation occurs, just think of the flux linkages to be a one-dimensional function of the currents. Just any sort of function as given like by this sketch here. This could be just any nonlinear function. In a real implementation, that could be a polynomial fit, or a sinusoidal fit, or a lookup table, whatever. It doesn't really matter. Important message, saturation means flux linkages become one-dimensional functions. But there's a second effect, and the second effect is called cross-coupling. And that's kind of a weird thing, because the D and Q reference frame has a 90-degree angle in between them. So if I change anything in the Q direction, this shouldn't influence the D axis. But now I say it does. Why does it? What is the physical effect behind it? And we can analyze that by the means of this little sketch here. In red, we see a D flux line. It's given here. And in blue, a Q flux line. And you can see that they share a common flux path here in the stator yoke. And this is exactly how they couple. Now let's say we fully saturate the D-axis. So this changes the magnetics here in the stator yoke. And that's why the Q-axis sees a different magnetic circuit. That's the physical reason for that effect. Again, how can you model that? Let's keep it simple. You can just think of the flux linkages to being two-dimensional functions of both current components. So the D flux linkage not only depends on the D current, but also on the Q current. That's it. This is exemplarily done like here. This is an FEM calculation of such a motor. You see the Q flux linkage, and you can clearly see the saturation effect right at the back here, and that the plot gets distorted with changing D current, and this is due to the effect of cross-coupling. So if you consider saturation and cross-coupling, this means you get two-dimensional flux linkage functions. And now we have to put these in our system equation. And just for repetition, the system equation is given here. It's here in the back. It's quite simple. You just put this nonlinear two-dimensional function in here, and you're good. But here, you have to differentiate this function. And that's kind of a thing. With the means of higher mathematics, not really a problem. It comes down to the differentiation of a multidimensional composite function, which is nothing else than the calculation of the total differential. I know that's some math now, but let me explain it real quick. So you have to differentiate the flux linkage. That's this. And we can calculate that with this equation. So let me explain it. So what we ask ourselves, how much does the D flux linkage change within one time step? And you can calculate that by how much does the D flux linkage change with the D current multiplied with how much the D current changed itself, plus how much did the D flux linkage change with the Q current multiplied with how much did the Q flux current change itself. That's just it. Not that complicated. And now I use some abbreviations for these partial derivatives here. And these partial derivatives are called differential inductances. I just use this in the following, and they are, again, two-dimensional functions of both currents. And this is nothing new, like also like 15, 20 years old. Like Melkebeek was, like, I think, the first who did that. All right, so let's put this into this equation, and there we go. This is the system equation that takes saturation and cross-coupling into account. And I want to, again, like motivate and explain like which part of the equation gives you which physical effect of the machine. So that's why I multiply the first equation with the D current and the second equation with the Q current. I didn't change anything, but that's just an equivalent equation. But from there we go to the powers. So what you now see is a power equation. And now let's look at like which part of the equation actually gives you which part, which physical effect. So the first here is a voltage multiplied with the current. This is obviously electric power. So this is the electric power we supply by the grid, or that we push back into the grid. And this gets split up in three processes. The first one, it's quite obvious, Ri square, ohmic losses. So that's a loss process that gets electric energy back to thermal, transforms electric energy to thermal energy. And then there's a second process, like all this with the differential inductances, that transforms electric energy to magnetic energy and vice versa. And the last process right here, this is the one we're actually interested in. This is our motor. This is the transformation of electric energy to mechanical energy, or the other way around. This completes like the electric model of such a permanent magnet synchronous machine. And now we have to take a look at the mechanic part of such a model. For that, we have to calculate the torque. And this is really simple. It's just the power balance of this equation, because the mechanic power is just the sum of that. And mechanic power is torque multiplied with speed. So if you want to get the torque, it's the power divided by the speed. And here omega is the speed. So just like keep that and that in your mind, add that up. And what you end up with is this equation. This is just the torque. It comes from the power balance of the electric equation. And just to make it really complete, that's the Newton's equation for rotational motion. Not really important. I really like this little picture, and I want to make it complete now, because obviously you can also transform magnetic energy directly into thermal energy, and that's called ion losses. You can also transform magnetic energy directly into thermal energy. That's called friction. And then there's one thing missing, and this is a process right here. You can also transform magnetic energy directly into mechanical energy, and the other way around. But this effect only occurs if you take spatial harmonics into account. Because we neglected them. This was one of my assumptions. I cannot cover this really. Just to make it complete, I like this picture. This is what any motor would look like. So whatever book you read, whatever presentation you see, whatever paper you read, doesn't matter. It's only a mathematical rephrasing of this picture. All right. This completes the modeling part. So now we have model parameters in this model. The flux linkages, the resistance, and so on, and we have to identify them. So how can this be done? Before I do that, let me real quick introduce my test bench that I want to use for all the measurements in the following. I use self-built power electronics based on skip modules that switch at a frequency of 8 kilohertz. My control algorithms are calculated on a DSP by Texas Instruments. This is a really fancy, good, like expensive DSP. For the controller I show you in the following, this is really simple controller. So the DSP idles most of the time when it calculates these really simple equations. I can see this here. This is the power electronics, and there behind this is like the load machine, and way there in the back is the test machine. My motor in the test is produced by Brusa. It is an automotive traction motor, has a power of around 100 kilowatt, and it has strongly nonlinear magnetics. It's water cooled. You can see that right here. So this is the motor on the test, 100 kilowatt, and there, this in the back, that's the water cooler. So how can we identify the parameters of that motor? First, stator resistance. That's totally straightforward and simple. Just the motor stands still, do a DC measurement using 4-wire sensing. There you go, you have the resistance. The two-dimensional flux linkage functions are also not that complicated. For that, you have to operate the machine stationary at constant speed. When you do that, you can rephrase the system equation to that form given here. So you can calculate the flux linkage by the difference here divided by the speed. The voltage can be measured. The resistance, we already know that from this measurement. The currents can be measured. Speed can be measured. And this is the way you can calculate it, given for the motor and test in these two little graphs. So these are actual measurement results. One thing, you kind of have to make sure that your machine is in thermal equilibrium while you perform the measurement, so that the resistance, which is obviously temperature dependent, is valid for your stationary measurements here. If you would be interested in these differential inductances, you can just calculate them as partial derivatives of these two lookup tables or flux linkage functions. And this is it. This completes like the identification of the model parameters. All right, so now let's use this model to control the machine. But before we get into this, let me give an overview and classification of control methods in general. Because the first question you can ask yourself is, like, what variable of the machine do I actually want to control? I could control the currents, that's CC, our current control. You could also directly control the torque, that's DTC, direct torque control. Or you could control the speed, that's DSC, direct speed control. That's like one dimension. The second dimension is, what method do you use to control this variable? Yeah, you could use a linear controller, hysteresis-based, fuzzy logic, sliding mode, whatever. Like predictive type controllers like MPC means model predictive control. And at all these intersection points, there are possible controllers, and I just add exemplarily some examples. It's definitely not complete, this list, but just like to show the basic idea. One thing you probably know from school is a linear current controller. That's the standard PI controller that like everybody that deals with electric motors gets taught in university. Another thing you might know, because it's in wide industrial application, is the work of Debbenbroek. It's ABB. Debbenbroek patented it, and ABB has a license on it and uses it to control their induction motors. It's a trajectory-based direct torque controller. In the US, Professor Lawrence, he's a famous guy in control of machines. He did a lot of work like in deadbeat direct torque controllers also. And what I want to do in the following now, I said I want to really keep it simple. I want to stick with, again, like a linear-based PI-type controller and directly control the machine currents. I don't change much. I just make little adjustments to make such a PI controller suitable for these nonlinear machines. What does the control structure then look like? Totally standard. Nothing changed, basically. You have some sort of reference values. You have measured values. You compare them, get a control deviation. This control deviation is fed to a controller that uses this control deviation to calculate a voltage that should be applied to the machine. This is back transformed to the alpha beta frame, back transformed to the theta voltages, fed to a modulator that puts the gate signals on the power electronic, and the power electronic physically applies this voltage to the machine. This is 100% totally standard. Like a lot of controllers run exactly with this scheme. So let's skip with that. Let's keep that and zoom into this controller and take a look at what a linear PI controller actually looks like. So this green picture is a zoom in of this controller here. And this is a standard linear PI controller. And you can see it has three parts: a PI part, a decoupling part, and a voltage limitation part. Why does it look like that? For that, we have to look at the equation we already developed. This is our linear system equation. And you can see that with this induced voltage in the back, these two equations are cross-coupled. And we want to remove that. And we can remove this by a feed-forward calculation of the induced voltages. And this is the decoupling part. So we just calculate that, add it up, and this removes this influence. The left over here is just a PD1 element, or for both axes. Like it's a PD1 element for the D and a PD1 element for the Q. And from linear control theory, we know that a PD1 element can be controlled by a PI controller. That's it. Well, but now I said this linear equation isn't valid. So we have this nonlinear equation. So what actually goes wrong if we use our linear PI controllers to control a nonlinear machine? Different things go wrong. The first is that this inductance here, this is operation point dependent. So in a nonlinear machine, this time constant here, this varies all the time. So we get errors due to that if we use just like one distinct inductance. The second thing, this dynamic cross-coupling feature here is totally ignored by linear equations, so we will get error due to that. And the third thing is that our decoupling here is not correct, and that's why we get decoupling errors. And this will yield a lot of things. It really depends on your machine and your controller and a lot of other stuff. But in general, you get current overshoots or even overcurrent shutdown. That's what I got a lot when I started off like with dealing with these kinds of machines. Like if you do it wrong, you get overcurrent shutdowns all the time. You get instabilities, oscillations, and in general, inferior dynamics of such a controller. And now I want to show you a really simple and easy approach to deal with that problem. What I want to do is I want to consider these time constant changes, and I want to remove the decoupling errors. I leave this dynamic cross-coupling feature. I don't take this into account. It could be taken into account. It has been done. But this is more an academic thing. It's not so important for an industrial application. That's why I leave this out. So let's do that and actually look at this advanced kind of PI controller. First of all, this is the standard that everybody uses like in millions of applications, and we have to add two little things. The first is we have to add this two-dimensional function of the flux linkage, which is a lookup table, and we use that to adjust our control parameters. That's the first thing. The second thing we have to do is we have to precisely decouple and therefore do a flux linkage prediction. So we have to take care of these two things, and then we are done. Okay, so how can we adjust the control parameters? It's actually not very complicated. You have to calculate an effective inductance for each time step of the controller. And this can be done by the formula right here. It can be proven that this effective inductance is nothing else than the difference from 2 flux linkage lookups divided by the currents. You have to just believe that for now. I don't want to go too much into detail here, but it's definitely doable. You can see it's really simple to calculate. It's like one line of code. Do this difference, do this division, there you go. And then just put like this effective inductance in your control parameters. So let's say you have a PI type controller and your controller function would look like that. There's the proportional part, there's the integral part. You just adjust the proportional part by putting this effective inductance right in here for both axes. There you go. The integral part, as you can see, doesn't even change. This is the only thing you can do. Like 2 lines of code. There you go. Decoupling errors. For stationary operation, it's actually totally simple. You just use the lookup table for decoupling. There you go. It gets a little bit more complicated when the current changes. Because if the current changes, this induced voltage changes all the time. And by that, you have to, like, that's what you should do. Let's say this is for one time step the induced voltage. This is the induced voltage at the next time step. Just predict these 2 values. It's just like this formula. It's again just a rephrasing of the system equation, and decouple with the average value in between the 2. Again, really simple equations that can be put in any microcontroller. Not that complicated. All right, I think that's all we need. So now we can look at the performance of such a controller, and if the model that I developed with you together is actually valid. And on the left, you see for a torque inversion of 100 Newton meters at 1,000 turns per minute, you see the simulation result of the model. On the right, you see the experiment. When I first saw that, I was really surprised. I would have never expected such a model to be that accurate. You can clearly see the nonlinearities of the system. So you can see the current steps are big if the current is big due to saturation. And if the current is small, these steps become smaller. The reference value of the D stays constant here, but you see changes in the D current. And this is due to the dynamic cross-coupling feature that we neglected in the controller. That's why we see this difference here. You see very good consistency of the simulation in the experiment. As I said, I was like amazed. I would never have expected a model to be that accurate. So the simulation model is definitely valid that I showed you here. And there's another important message on this slide. And this is that you can actually parameterize such a model with stationary measurements of the flux linkages. And by doing that, you can predict the dynamics of the system. This is possible and proven by that plot. It's just like one as an example. I could show you like a lot more, but I think that's rather boring. Again, how does such a controller perform? Again, I could show like dozens of jumps and whatever. I just chose 2. It's a current step here and a torque step right here where both reference currents change. Again, you can see the nonlinearities. The performance is totally satisfactory. There's no overshoot. And also in other operations points, there is no overshoot, although the machine is strongly saturated. Like for this current jump, it's strongly in saturation. And it totally works like that. Although it's just, we just added like 2 or 3 lines smart code. One important thing that I want to like also stress on that slide. If you go to conferences and people from academia, they propose really fancy control algorithms, very complicated, and they always compare themselves to a standard PI. And they say, well, the standard PI looks like that, so the step response might look like that, or might overshoot like that, and my response looks like this. And that's why I'm so much better. Not true. It's not true. The perfect controller for this step here would look exactly the same at the beginning from here to here. Why? Because the machine is operated at the inverter output voltage limit. You work at the physical limit of the system. The controller cannot be any faster. What would change is that a better controller would perform a deadbeat step from here on the reference value here. So this is a typical PI response, and that would be performed the deadbeat step. Is that so important for industrial applications? This means we get our reference values, let's say 3 control periods before. That's in the order of 500 microseconds. Is that so important? For doing all these other calculations, I don't think so. So if you break it down, and this is maybe the most important message of this talk here, if you do a PI controller correctly, we know it, it's simple, everybody knows it. It's definitely sufficient to control these nonlinear machines. All right, let me sum it up. So I showed that if you have small light machines that have a high power density, you get a low weight to power ratio, and this can be done, or is usually done, by getting strongly nonlinear magnetics of such a machine. These strongly nonlinear magnetics are caused by 2 things, by saturation and by cross-coupling. and they can be modeled by two-dimensional flux linkage functions. You can then use a standard PI controller and do some easy adjustments by first an online modification of the control parameters, and second, a precise decoupling to successfully control these kinds of machines. All right, this was my last slide. I thank you for your attention, and I'm happy to answer any questions.
Jan, thanks for a very interesting presentation. Just two brief questions.
Can you speak a little louder? I really cannot hear you.
Thanks for your interesting presentation. Just two brief questions. I'll take the second one first, if that makes sense. Would it be possible to get a copy of the presentation?
Yeah, sure.
Yeah.
I'll give you a PDF version of the presentation.
Sure, that would be great. My main question was that you mentioned about some of the complicated control schemes that are proposed by academia. Often they're very sensitive to real-world variation in the plant parameters. Could you say a little about how your scheme is, what its sensitivity might be to the real-world variation that we see in the parts?
Yeah. So there are two things that this scheme is sensitive about, like if the resistance is wrong, this is one thing, or if these flux linkage functions are wrong, that's the second thing. In these kind of machines, the resistance is usually really, really small in comparison to the induced voltage. So even if you have like the double resistance, it doesn't really change much. So the resistance sensitivity or the total performance is really low, and that's why this is not so important. That's the first part of the answer. Second part, what about the flux linkages? And there you can really break it down to one thing. If you overestimate your flux linkage, let's say the real flux linkage of the machine is smaller than the one that you think in your model it is, if you overestimate, your controller will overshoot, and this is critical. If you underestimate the flux linkage, your controller will just be a little slower than it should be. And this is the answer to the question. Of course, there is a sensitivity, but in our measurements, and we measured like a lot, it was never critical if you underestimate the flux linkage a bit. Because the reason, why does the flux linkage change at all? The Q flux linkage in general does not change. Even the machine heats up or whatever, if the machine ages, it doesn't change that much. What changes is the D flux linkage because of the permanent magnets. If they heat up, the D flux linkage gets reduced. It's like it could be modeled like an offset, or if the magnets age, this is also like a reduced D flux linkage. So if you have a good controller, there's just underestimate, that's a simple solution, or a more complicated solution, that's what I do in my work, just use a flux linkage observer and observe the flux linkages online and track these changes and put them in the lookup table. So these are the two possible solutions to that kind of problem. Any other questions? If not, we can all go to lunch. All right, I think that was it. Thanks again for your attention. And I hope it was kind of interesting for you guys. All right, bye.